Good day, students. The third lesson of Module 4 is about periodic trends. This is about the periodic variations in the physical and chemical behavior of the elements. Okay, before we start, let us recall the structure of the atom. So, in the atom, we have our nucleus in the center. In the nucleus, we have our protons, which are positively charged, and our neutrons, which are neutral, or they don't have charges. Surrounding that um, nucleus are electrons, and electrons are negatively charged. Okay, these electrons, since they are negatively charged, they are attracted to the nucleus because in the nucleus we have our positively charged protons. And electrons, since they have the same charges, they tend to repel each other. Okay, opposite charges attract, same charges repel. So here, and for our first predict trend, we have effective nuclear charge. What is effective nuclear charge? This is the nuclear charge. When I say nuclear charge, that's the charge of the nucleus. So since our nucleus has protons, so that is the positive charge. And the positive charge felt by an electron from both the actual nuclear charge, which is equal to the number of protons, and the repulsive effects of the other electrons. So effective nuclear charge takes into account the actual nuclear charge, the number of protons, minus the repulsive effects of the other electrons. So for the formula of the ZF is our effective nuclear charge. It's equal to Z, which is the actual nuclear charge or the number of protons. So this is the number of protons, which is also equal to the atomic number. S is our shielding. Again, effective nuclear charge takes into account the actual nuclear charge, the Z, and the or minus the repulsive effects by the electrons. That is why it is called the net positive charge. No? After getting the difference, we have the net positive charge felt by the electron in a polyelectronic form, meaning we have many electrons. So we have the so-called shielding effect. Remember, our ZF is equal to Z minus S. So S is our shielding. When we say shielding effect, this is the decrease in attraction between an electron and the nucleus in any atom with more than one electron shell. Again, the electrons are negatively charged, whereas our nucleus is positively charged because of the presence of the protons. So these electrons again are attracted towards the nucleus, towards the proton in the nucleus. Now what happens is um, these electrons tend to shield each other, no? So their attraction towards the nucleus then is decreased. Okay, here is an experimental evidence or proof of this. This is a helium atom which has two electrons. According to experiment, it takes 3.94 times 10 to the negative 18 joules to remove the first electron, whereas it takes 8.72 times 10 to the negative 18 joules to remove the second electron. Why is this so? Now, when there are still two electrons present in the atom, again, there is shielding. So this electron, for example, shields this electron. What happens then is there is decrease in the attraction between this electron and the other electron. So that makes it easier, because there is decrease in attraction, so it makes it easier to remove that electron. Now when this electron is removed, only one electron remains, so there is no other electron to shield this electron from its attraction towards the nucleus. So what happens then is its attraction is increased. Because of that, it takes a larger amount of energy to break that attraction and remove this electron from the atom. So that is shielding. Now if this is our nucleus, for example, we have our core electrons. In our second energy level, we have additional electrons, for example. When we compare the shielding, the shielding of electrons which are on the same energy level is lesser as compared to the shielding of the electrons by the core electrons. For example, um, the electrons here, for example, shield less effectively or less as compared to the shielding by these electrons. So since these electrons are in the first energy level, they are more attracted, no? Because they are closer to the proton, for example, or to the nucleus. So they are more attracted to the nucleus. Because of this, the attraction by the electrons in the second energy level are decreased or is decreased, no? Because they are farther from the nucleus. So they are effectively shielded by these two electrons, or by these core electrons. The trend for effective nuclear charge is that it increases from left to right, so, and also from top to bottom. So an example here, we have from lithium to neon. This is our lithium here. This is our neon. As you can see here, the ZF increases from lithium to neon. Now, why is this so? Recall that our formula for effective nuclear charge is ZF equal to Z minus S. Z is our, what is this Z? This is our number of protons, which is equal to the atomic number. Now, what happens to the atomic number as we go from left to right? It increases, right? It increases by 1. So this value then increases from left to right. Now, what about the value for shielding? The value for S. As I've said earlier, we have our nucleus, for example, then we have our first energy level, which has 2 electrons. So only 2 electrons can occupy in the first energy level. And the second energy level, we have how many electrons it can occupy? We have 1, 2, 3, 4, 5, 6, 7, 8. So as we go from left to right, we add electrons, but the added electrons are actually on the same energy level. So therefore, it is not much effectively shielded. So therefore, at the shielding, the value of S is not much large, no? So because of that, this value here, ZF, then increases from left to right. Again, from left to right, the value of Z increases. So from 3, 4 up to so on and so forth. The S value does not increase that much because the added electrons are on the same energy level and is not effectively shielded by the other electrons. Okay, now from top to bottom, from lithium down to cesium, the effective nuclear charge also increases. Why is this so? Although, as we go from top to bottom, we have new energy level, and the electrons here are farther from the nucleus. So, the shielding supposedly is increased because we are now adding electrons in another energy level. So, it's much farther from the nucleus. However, as we go from top to bottom, as you can see here, the atomic number increases also much larger, from 3 to 11 to 19 and so on. So the increase in the amount of Z is much larger as compared to the value of S. That is why from top to bottom, ZF also increases. Okay, now how do we calculate effective nuclear charge? Again, our formula for effective nuclear charge is ZF equal to Z minus S. Z is the atomic number, so we already know this. So what we're gonna do is we calculate for the value of S. So the first step in calculating effective nuclear charge is to rewrite electron configuration in this manner. So we have 1s, so first energy level, then we have S and P together, 2s and 2p, 3s and 3p, and we have 3d, 4s and 4p, and so on and so forth. So after writing the electron configuration in this manner, we calculate next the value of S, or the shielding, using Slater's rules. What is Slater's rules? Electrons to the right have zero shielding factor, do not have shielding factor, because they're the ones shielded by the previous electrons. So the rule is, for N, this is 1, this is 2. For NS and NP valence electrons, electrons in the same NS NP group contribute 0.35 shielding factor, and electrons in the N-1 contribute 0.85 shielding factor. So let's remember this. This is 3. Electrons starting at N-2 groups and so on contribute 1 shielding factor. Okay. For ND and NF valence electrons, electrons in the same ND or NF group contribute 0.35 shielding factor, while the remaining electrons to the left contribute 1 shielding factors. Again, this is our formula for ZF. Okay, let's have an example. Calculate the effective nuclear charge felt by the differentiating electron of oxygen. So when we write electron configuration of oxygen, we have 1s2, 2s2, 2p4. So the first step is we rewrite it. We start with the 1s, we have our 2 here, then 2s, 2p. We have 2s, 2 plus 4, so we have 6 total here. Okay, for the solution, the differentiating electron of oxygen is in one of those in the 2s and 2p group. That means we only count 5 electrons in that group. As I've said before, the electron to the right have 0 shielding factor, so we minus 1 from the total electrons. Okay, so we start with the 2s and the 2p, so minus 1, so we only use 5 number of electrons times 0.35. The rule is, if it's in the same NSNP group, let's go back. In the same NSNP group contribute 0.35 shielding factor. So we multiply the number of electrons by 0.35. If it's N-1, we use 0.85, and if it's N-2, we use 1 shielding factor. So where is it now? So we have 2s2p, we minus 1 this. We use only 5 number of electrons times 0.35 because it's in the same NSNP, plus our oxygen again is 1s2, 2s2p, 6. So we have 5 times 0.35. In the N-1, this is 2 minus 1, so this belongs to the N-1. So we have 2 times 0.85. If it's in the same NSNP, it's 0.35. If it's N-1, it's 0.85. Okay, so we add the 2, then we get S value of 3.45. So to compute for the effective nuclear charge, the atomic number of oxygen is 8. So you have Z minus S. So 8 minus the calculated value for S, which is 3.45. The ZF then is 4.55. Okay, another example. Calculate the effective nuclear charge felt by the differentiating electron of aluminum. So the electron configuration of aluminum is 1s2, 2s2, 2p6, 3s2, 3p1. So we rewrite that as 1s. Then we have our 2 here, 2s and 2p. So we add these 2, we have 8. Then we have 3s, 3p. We add these 2, we have 3. Okay. Again, the last electron don't have shielding factors. Our last electron is here, so we minus 1 from the 3s3p, we only use 2 electrons. Okay? So, ang rule is that if it's in the same n as np, we multiply this by, what is it, 0.35. So, it's same n as np. If it's n minus 1, so 3 minus 1 is 2. So, this is in the n minus 1. So, we multiply this by 0.85. And if it's the electron is in the n minus 2, so 3 minus 1 is, minus 2 is 1. So, we multiply this by 1. Okay. So, here we have 2 times 0.35, 8 times 0.85, and 2 times 1. So, the total value of S is 9.5. To get the effective nuclear charge value, again, we have this formula Z minus S. The atomic number of aluminum is 13. So, we have 13 minus the 9.5 calculated value for S. So, we get effective nuclear charge value of 3.5. For our third example, calculate the effective nuclear charge felt by the differentiating electron of titanium. The electron configuration of titanium is, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. Now what we're going to do is we rewrite it. We start with the first energy level, followed by the second energy level, then the third, and lastly is the fourth energy level. Okay. Now, the differentiating electron of titanium is in one of those in the 3d2 group. Remember that we are using differentiating electrons. So, before we rewrite the electronic configuration, the last orbital is filled is in the 3d2. Okay, so that is where our differentiating electron is. Okay, but when we rewrite that, the 4s2 is actually on the right side, so we will disregard this. And since the outer electron doesn't have shielding factor, so this is minus 1, so we only use 1 of the 3d, and then 8 of 3s3p, 8 of 2s2p, and 2 of the 1s. Now, since the differentiating electron of titanium is in the D, so we use the rule for the NS and D, ND and F configuration. Where is it? Let's go back so that we can recall the rule. Now, for ND and NF valence electrons, electrons in the same ND or NF group contribute 0.35 shielding factor. The remaining electrons contribute 1 shielding factor. So therefore, okay, in the same N as ND, so we only have this 3D. So we multiply this 1 by 0.35, whereas the remaining, so 8 plus 6 is 14. 8, this is 8 pala. 8 plus 8 is 16, plus 2 is 18. So we have remaining of 18 electrons, which we will multiply by 1. So to compute for the shielding, we have 1 times 0.35 plus 18 times 1. So the total shielding is 18.35. To compute for the ZF, or the effective nuclear charge, we have Z minus S. The atomic number of titanium is 22. So we have 22 minus 18.35. The effective nuclear charge of titanium is 3.65. Okay, for the next periodic trend, we have atomic and ionic radii. The trend for atomic radii from left to right is that it is decreasing. Why is this so? We will look at or refer to the value of effective nuclear charge. Recall that the effective nuclear charge from left to right increases. So What is effective nuclear charge again? It is the net positive charge felt by the electron. So because of the increasing net positive charge felt by the electron, the tendency is the electrons are pulled towards the nucleus. Because of this, we have decreasing size of atomic radius or radii as we go from left to right. Here an example, we have from lithium to beryllium to boron, for example. The sizes, this one in gray, decrease from left to right, again because of the effective nuclear charge. The electrons, as we go from left to right, are more attracted towards the nucleus, so that results to a smaller size of the atom. Okay, for ionic radii, the trend is it decreases from left to right. What do you mean by ions? We have cations and anions. So when do we form cations? Cations are positively charged ions. Remember that for a neutral atom, we have equal number of protons and electrons. So when do we form cations? We form cations when the atom loses electrons. So when the atom loses electrons, there are now more protons than electrons. That is why we have positive charge or positive net charge. That is why we form cations. Now, as we go from left to right, for example, by the way, we only compare ionic radii of isoelectronic ions. Where do we write this one here? Isoelectronic ions. When I say isoelectronic ions, they have the same number of electrons. Okay. For example, the isoelectronic ions here, we have our lithium, beryllium ion, and boron ion. So, why are these electrons isoelectronic, by the way? For lithium ion, its atomic number is 3. Okay, so this is 3. For beryllium, its atomic number is 4. While for boron, its atomic number is 5. Now, when the lithium atom lose one electron, so its positive charge is, or it has positive 1 net charge. So what happens to the number of electrons when the lithium loses 1 electron? It becomes 2, of course. When beryllium atom loses 2 electrons, the cation form is beryllium 2 plus because it loses 2 electrons. So the remaining electrons then is 2. For boron, it has 5 atomic number. When it loses 3 electrons, the remaining electrons now are 2. So look at here, we have 2, 2, and 2. That is why lithium ion, beryllium ion, and boron ion are isoelectronic ions. They have the same number of electrons. Oxygen and fluorine are also isoelectronic ions. Oxygen has atomic number of 8, whereas fluorine has an atomic number of 9. So when do we form anions? Anions are formed when a neutral atom accepts electrons. So there are now more electrons than protons. That is why we have a net negative charge. So when an oxygen atom accepts 2 electrons, it will have a 2 negative net charge. So what happens to the total number of electrons after oxygen gains or accepts 2 electrons? It becomes 10. For a fluorine ion, if it accepts 1 electron, so its net charge now is -1, and the total number of electrons is 10. So they have the same number of electrons. So these two ions are isoelectronic. Okay, let's go back to the cations. As we go from left to right, from lithium ion to boron, our atomic number increases, right? We still have 3 because it's the electrons that are being lost. The protons, the number of protons are the same. So we have 3, 4, and 5 number of protons, whereas the electrons are being lost. Remember that our effective nuclear charge is ZF equal to Z minus S. So as we move from left to right, our value of Z increases. The shielding, on the other hand, decreases because we are removing electrons to form these ions. No? From lithium to boron, the shielding decreases because there are now less number of electrons. What happens is the electrons are more strongly attracted to the nucleus because we have more protons and electrons, and as a result we have smaller ionic radii, no, for cation. So if the cations isoelectronic if the isoelectronic cations increases in the charge, in its charge, we have from smaller positive charge to larger positive charge, the ionic size decreases. Again, because we have now more protons and electrons, so the electrons are more attracted towards the nucleus, and that results to a smaller size. No? The electrons are pulled towards the nucleus. For the anions, isoelectronic anions, again, anions are the result when an atom gains electrons or accepts electrons. So recall that electrons repel each other because they have the same charges. Now, when, for example, in fluorine, when it gains or accepts electron, there are additional repulsion of electrons. What happens to oxygen when it accepts 2 electrons? No? There is way more repulsion as compared to fluorine. That is why for the isoelectronic anions, the higher the negative charge, the larger the repulsion, the larger is the size. Okay? So that is the trend for ionic radii. From left to right. Okay. For the trend of the atomic and ionic radii from top to bottom, since as we go down the bottom, from top to bottom or down a group, there is increasing value, or there is increase in the principal quantum number. So we have additional energy levels. For example, this is our nucleus. We have the first energy, second energy, third energy level, and so on and so forth. So as we go down a group, the energy level increases, and with this there are more electrons being added to the value of n, or to the energy level. With these additional electrons, the repulsion is increased. No? There is larger repulsive forces among the electrons. Because of this, the size of the atom or the ion increases. No? So it's the repulsion of the electrons which increases the size of the atom or the ion from top to bottom. Okay, so you can see here their sizes increase from top to bottom, going down a group. The next periodic trend is ionization energy. So this is the energy required to remove electrons. So a factor of this is the size and the effective nuclear charge. So for ionization energy from left to right, the trend is it's increasing. Why is this so? Okay, from left to right, recall that our effective nuclear charge increases and our atomic size or radius decreases. Why is this again? Why does atomic size decreases from left to right? Because the ZF increases. No? The electrons from left to right felt more the net positive charge of the nucleus. So they are more strongly attracted towards the nucleus. They are pulled towards the nucleus. Now when our ZF, or when the electrons from left to right are more attracted towards the nucleus, it would be hard to remove these electrons. That is why from left to right, as we go across a period, the ionization energy increases. Now going down a group, although the ZF increases from top to bottom, again the electrons are added in outer energy level. Okay, so as the electrons are farther from the nucleus, their attraction towards the nucleus is less, no, as compared to those in the lower energy level or in the core electron. So because of this lesser attraction of the electron towards the nucleus, it would require less amount of energy to remove them. That is why the trend for ionization energy from top to bottom is decreasing. So here we have from left to right, ionization energy increases, and from top to bottom, it is decreasing. The next periodic trend is electron affinity. So this is the energy evolved when an atom accepts electron. Electron affinity is like the tendency of the atom to accept electron. How much does the atom want to accept electron? The trend for electron affinity is across a period or from left to right, it is increasing, while from top to bottom or down a group, it is decreasing. Okay, why is it that across a period, electron affinity increases? We call that as we go from left to right, ZF or effective nuclear charge increases. That means the electrons, as we go from left to right, felt more the net positive charge of the nucleus or the net positive charge. So that is why from left to right, the electron tends to pick up electrons easily. No? They tend to accept electron from left to right because, again, the electron, as we go from left to right, feel more the net positive charge, no? Or the positive charge of the nucleus. Now, as we go from top to bottom down a group, the electrons being added are now farther from the nucleus. So, because of this, the atom, no, does not tend to pick up that electron easily because of the lesser attraction between the electron and the nucleus. Because it is farther, the electron is now farther from the nucleus. So this is the trend for electron affinity. From left to right, it increases. From top to bottom, it decreases. The next periodic trend is electronegativity. This is the ability of bonded atoms to attract shared electrons. So when I say shared electrons, it is actually in a covalent bond, which we will discuss in the next module. The trend for electronegativity is increasing from left to right and decreasing from top to bottom. Now, why does electronegativity increases from left to right? This electronegativity is actually associated or connected or related with electron affinity and ionization energy. Ionization energy and electron affinity. Okay, so my trend. What is the trend for ionization energy and electron affinity as we go from left to right? Ionization energy increases from left to right as well as electron affinity, which means to say that as we go from left to right, it would be hard, no, to remove the electron from the atom, and we go from uh, as we go from left to right, the atom has larger tendency to accept electron, no, because our electron affinity increases. So because of that, the atom also, as we go from left to right, has the ability or larger ability to attract the shared electrons in a bond. Down a group, electronegativity decreases because ionization energy decreases. And the electron affinity decreases as well, so the electrons are not really tightly held, no? or there is less attraction between the electrons and the atom as we go down a group. So it's also the ability of the valent atoms to attract the shared electrons also decreases as we go from top to bottom. Okay, here is the trend for electronegativity. Again, from left to right, it is increasing, and from top to bottom, it is decreasing. Our most electronegative element is fluorine. So it has high electron affinity, which means it tends to pick up electrons easily, and it has high ionization energy, which means it does not lose electrons easily. So that's why it has high electronegativity. Those elements on the left and at the bottom, for example, have low electronegativity because they have low electron affinity and low ionization energy. So this is a summary of the trends in the periodic table of elements. Our atomic radius and ionic radius from left to right is decreasing, and from top to bottom is increasing. Electron affinity, ionization energy, and electronegativity all increase from left to right and decrease from top to bottom. Okay, let's have some examples. First example, arrange sodium, strontium, beryllium, boron, and magnesium in order of increasing atomic size. So let's look at sodium. Where is sodium? Sodium is here. Beryllium, strontium is here. Beryllium is here. Boron is here, and magnesium is here. Okay. Arrange in order of increasing atomic size. That means we start with the smallest atomic size down to the largest size. What is the trend for atomic size? It increases from top to bottom and decreases from left to right, which means to say the rightmost is is the element with the smallest size. So we start with, let's put our answer here, with boron, followed by beryllium. Then we go down a group. The left one is, or the one on the right is magnesium, so that should have the smaller size as compared to the element on the left, which is sodium. And our largest atomic size is strontium, okay, from the given. Okay, so again, when we say increasing, we start with the smallest size and we end with the largest size. Okay, for first ionization, energy, electron affinity, and electronegativity, all of these three have the same trend. From left to right, they are increasing, and from top to bottom, they are decreasing. So let's put here B to D. Okay, so we start with the one with the smallest ionization energy, electron affinity, and electronegativity. So it's actually the opposite of letter A, no? Because the trend for atomic size is opposite with the trend of the three. So from top to bottom, they are decreasing. So we start with strontium. Okay, that should be the one with the highest ionization energy, electron affinity, and electronegativity. That should be the one on the right and at the top. So we have here our boron. Okay, so from strontium we go up. Sodium should have smaller value as compared to magnesium, followed by beryllium, and lastly boron. Okay, for the second example, we have the elements potassium, barium, bromine, iodine, arsenic, and cesium. So which of these, instead of arranging, let's just identify which has the highest, the largest atomic size and the highest first ionization energy, electron affinity, and electronegativity, and the smallest size and the largest, smallest first ionization, electron affinity, and electronegativity. Okay, again, the trend for atomic size is that it increases from top to bottom and decreases from left to right. So therefore, the one with the largest size that we expect should be on the bottom and on the left. Therefore, our largest size should be cesium, so largest. The one with the smallest size should be on the top and on the right. So we expect bromine not to be the one with the smallest size when we base on the general trend. Again, the one we are referring here are the general trends in these different properties. When it comes to the first ionization energy, electron affinity, and electronegativity, again, the three of them have the same trend. They increase from left to right and decrease from top to bottom. So the one that we expect to have large values for these three should be on the right and at the top. No? So therefore, we expect bromine to have the largest first ionization energy, electron affinity, and electronegativity. On the other hand, we expect the one on the bottom and to the left to have the smallest first ionization energy, electron affinity, and electronegativity. So that's it for the periodic trends.